So, today's discussion is on analysis of drive, draft and production calculations. Let us go to the next slide. Look at this diagram. The gearing diagram of a ring frame is shown here. What you can see here, that there are many blue arrows, and these arrows actually indicate the motion transmission path from the motor to the various parts of the machine. This is a typical diagram that we have taken, and if we try to find out how the motion from the motor is going to the different organs of the machine, we need to know the path that the motion is flowing. Here is the motor as shown in this diagram. Okay. So, the motor is here, this is driving the machine pulley. So, this is the machine pulley, and the arrow shows the flow of motion from motor to the pulley. For the machine pulley, you see, if you trace it, here is a jockey pulley, and from the jockey pulley the motion goes through the belt to the spindles of the ring spinning machine. So, this is the way the motion is flowing from the jockey pulley, and you will see there are number of jockey pulleys which are there on this shaft, and from these jockey pulleys the motion is going to the spindles. On the other end, here is a set of gears which are there, and the motion goes from here to this, from there it is coming over here, flowing like this and taking this path, and you see as it is going here, from there it is coming to this particular gear. There the motion is actually splitted into two parts. So, one motion flows this direction, right hand directions, and the other motion is flowing towards the left hand directions. So, this side the motion goes to the drafting unit which is here, and from the right hand side the motion is actually going to the cam, the building motion of the ring spinning machine, which we have already studied, is going over here, and also going to the through this set of pulleys, it is going to the ring rail. So, the motion source is here, it is flowing in these directions and going from here to the drafting unit, also going from here to the building motion where the cam is there, and also going trying to drive the ring rail. So, this is how the motion is transmitted. So, whenever we look at the gearing diagram of any machine, we should try to understand how the motion is flowing from the main source, which could be a single motor, sometimes that could be multiple motors in the given machines, but we must try to understand the way the motion is flowing from the motor to different parts of the machines. From here we go to the next diagram, which is again the same diagram, we are showing it here, but here we are interested to know the direction of rotation of the gears and the pulleys, because we know that the entire drive has to be designed in such a way, so that we get the right speed of the different organs of the machine, and not only the right speed, we should also make sure that the different organs or different parts of the machines are rotating in the desired directions. Like let us say drafting rollers, all the drafting rollers should move in the forward direction, because I have to deliver the drafted product in the forward direction. Therefore, when we have 3 drafting rollers over here, they should be connected through a set of gears in this zone in such a way that the final direction of rotation of the front roller, the middle roller and the back roller are all in the same directions. Similarly, the spindle should also rotate in a direction so that we get not only the desired level of twist, but also the twist in the right directions. Like we all know that the twist in the ring spinning machine we get in Z directions. We always produce Z twisted yarns. So, let us try to see. Now, if we look at this here, the pulley rotates in this direction as shown by this arrow, and therefore, these two pulleys are connected by a belt, and hence the direction of rotation of both the pulleys are same. Then from here the motion comes over there, and here we have gears. So, when the gears are meshing each other, the direction of rotation of the driven gear is always opposite to that of the driving gears. This is what you should be very clear, that where pulleys are driving each other, the direction of rotation remains same unless we go for cross belt drive. You must have seen in some cases that we have cross belt drive where we can change the direction rotation of the two pulleys. Otherwise, the direction of rotation of the driver pulley and the driven pulley is always same. Whereas, when the two gears are meshing each other, between these two gears or these two gears, there are so many gears which are meshing in this diagram. When the gears mesh each other, the direction of rotation changes. The direction of rotation of the driver pinion and the driven pinions are in different directions. So, let us look at it. Here it goes in this directions because this is mounted on this shaft only. So, therefore, this is the driven pinion, it rotates in the opposite direction. So, the arrows are actually going against each other. That basically means that they are turning in opposite direction. So, this and this are mounted on the same shaft. So, their direction of rotations are exactly same, but this is meshing with this. So, direction of rotation will change. These two are same, here they will be different, and then these two are same again, but here now there is a pulley. So, we are turning this pulley and this pulley, because there is a connecting belt, the direction of rotation of these two pulleys are exactly same. So, the arrow directions are also same. From there the motion comes to this gear is mounted on the same shaft where the pulley is located, and therefore, rotational direction of pulley and this gear are exactly same. Now, this is meshing with this, the rotational direction changes, and on this shaft you have different gears. There are three different gears or pinions, and the rotational direction of this and this are exactly same. And when it meshes with this gear, the direction of rotation changes, and on this gear the shaft holds the front roll bottom roller, and therefore, rotational direction of this gear and the front drafting roller are exactly same. So, similarly, if we look at the way the direction of rotation changes, if you trace the path the way it has been shown here, you will find that the rotational direction of the middle drafting rollers and the back drafting rollers are all in the same direction, and that is what we wanted. So, the gears are not only numbered, their teeth numbers should be such that we get the desired draft. Not only that is important, we also have to make sure that they rotate in the right direction also. This is also important for us. Now, from here, as we said, the motion goes to the gets splitted from this gear, it goes in the right hand direction and the left hand direction also. So, in left hand direction the motion is this direction, from here it goes this gear, from there it is driving the cam, and therefore, this cam is pressing the building motion, is a part of the building motion, which there is a lever, we have already discussed these points. The lever moves up and down, and therefore, this arrow has a double head, which indicates that this particular lever is going up and down. So, from here the chain is there, chain is also going up and down. So, is going over a pulley, from there it is connected to the ring rail, and as a result what happens, the ring rail also moves up and down. So, this is how the motion is transmitted, and the directional rotations also, as we see it here, that we get them in the right directions. So, a full understanding of these two aspects are very necessary when you are actually walking in the shop floor, or while you are trying to understand how a machine really works. So, whenever you come across with a drive diagram of any machine, you should try to read the diagram properly, so that it will help you to understand the way the machine works, and therefore, whenever there is some fault in the process, you will be able to locate the source of the fault easily. From there we go to the spindle drive. Now, spindle drive, there are three types: tape drive, tangential drive and direct drive, as shown in the diagram. Now, we will see the force spindle drive as shown in the diagram. You see the two sketches you can are there in this particular slide, and this is going to make the understanding very easy. What we see here, that there is a pulley which we call them jockey pulley. So, this is the jockey pulley, or here this is the jockey pulley, the same diagram. So, the jockey pulley is, there is a central shaft below the machine on which number of jockey pulleys are there, and the jockey pulleys are connected to the spindles. So, therefore, a tape connects the jockey pulley with 4 spindles. So, this is known as 4 spindle drive, because one tape will run 4 spindles. So, how many tapes are required? It is 1/4 the total number of spindles. So, number of spindles therefore has to be such that it is divisible by 4, because we know that one tape is going to drive 4 spindles. It will be 4, 8, 12. So, it has to be a multiple of 4. 4 spindle drive generates less noise, and it also consumes less energy. This is the advantage that we have. You see that these are the 4 different spindles, and here is the tape which is running like this, as shown it here. So, one tape as it runs, it drives the 4 spindles. The angle of wrap around each spindle is roughly around 90 degree. So, with 90-degree wrap, the friction that is there between the tape and the spindle verb, that is sufficient to drive the spindle at a certain speed. Tapes, the advantage is that easy to replace. So, that is the biggest advantage of tapes, that they are easy to replace. And from there we go to the next type of drive, which is called tangential belt drive. The tangential belt drive, we have one single belt as shown in the diagram. This is one belt. See, this black line indicates the belt going like this around the machine. Here there is one single belt, or we may have 2 belts as shown it here. There is one side has one belt, the other side has another belt. So, and these small circles are indicating the verbs, and these ones, that green ones, are the pressure rolls. They are actually pressing the belt and ensuring a proper contact between the spindle verb and the tape. So, you see that the tape is in contact with the verb, and the contact is not really 90 degree, is less than that, and as we press the tape we make sure there is intimate contact between the belt and the verbs. One belt drives all the spindles of one side of the frame, thus two belts are generally required. The advantage is it eliminates drive component under the machine. We do not need so many jockey pulleys as we need in the case of 4 spindle drive, and there is less disturbance of air under the machine. This is another advantage we get. But the disadvantage is that if the belt breaks due to any reasons, all the spindles on one side becomes idle. This is the serious problem that we have to make sure that the belt never breaks. In case it breaks, all the spindle becomes idle. Whereas, in the case of 4 spindle drive, this is not going to be so, because if one particular tape breaks, 4 spindle will be out of order. The rest of the spindles will work and will give you the production. So, that way the production loss is going to be less when you go for 4 spindle drive. So, both the drives have got their own advantage and disadvantages, and the other thing is the single independent drive to the spindle by single motor is not very popular as of now, where each spindle is driven by a single motor, because you need so many motors in that case. That is what is not really very popular, or as of now not so much accepted by the industry. The spindles drive we have seen. Now, another important aspect of the spindle drive is that the spindle speed is varied throughout the bobbin build. That is, spindle speed from beginning to end of a particular bobbin building is not fixed, it is not constant. If it is not constant, means it is varied. How it is varied? That is shown by the diagram on the right hand side, where on the x axis what we have? Yarn wound percentage assuming full bobbin as 100%, and on the y axis what you have? Spindle speed in terms of RPM. So, the diagram is shown here, and if you see here, you look at this diagram, obviously you see there are speed is rising from beginning, and then again it is changing, remaining stationary for some time, again there is a jump, again stationary for some time, again there is a jump. That is how the spindle speed is varying. So, at the start of the spinning, what happens? The balloon is very long, because you have started winding at the bottom of the cup. The balloon is long. The winding on diameter is also very small, because we are actually winding on the almost on the bare bobbin, and therefore, what happens? Spinning tension is very large. So, the yarn is wound at much lesser speed at the beginning, otherwise there will be too many breaks. The whole purpose of changing the spindle speed with the increase in bobbin size is basically to ensure that we do not encounter too many end breaks. So, to avoid end breaks, we have to reduce basically tension, and the only way or most convenient way to change tension during spinning operation is the spindle speed. So, spindle speed, if we can reduce the tension easily. So, what we see here, the speed is raised sequentially, and when the spinning tension stabilizes, the spindle is turned at high speed as shown it here. That is, from in this zone you see half the bobbin has been built by the time we come over here. 48% of the package size has been built, 48 to 90%, that is the time when the machine is running at the high speed, which is in this case at 18,000 RPM. So, we will start at a very low speed of maybe around 16,000 RPM, and then gradually increase the speed. First jump is 5% change in speed, then not 5%, by the time we go almost, yes, 10% of the bobbin has been built, there is certain jump in spindle speed. We go from 16,000 rpm to 16,500 rpm, all right, and then up to a certain, almost up to 5 to 22% of the bobbin build, the spindle is remains stationary, we do not change it. Then again there is a jump, a slow increase in speed from 16,500 to 17,000. We slowly raise the speed. So, we reach, by that time 30% of the bobbin has been built, 30 to 40%, again there is no change in speed, and again we gradually raise the speed and we attain the high speed, which is 18,000 rpm. By the time we have produced almost 50% of the bobbin, and then we keep it stationary or fixed, and in the end we again reduce speed, because by the time we go to the end, the bobbin has, the balloon has reduced in size, the bobbin is almost built, but the end brakes suddenly rises in this zone. We will see that why does it rise, and therefore, we need to reduce the speed again. The nature of speed adjustment depends on the spinning conditions. The optimum condition is determined taking into account the yarn quality and the end brakes that we can sustain. How much brakes is permissible? What is the industry standard or what is the industry norm? Depending upon that, the optimum conditions is actually chosen. The yarn brake near full bobbin can be restricted by keeping the speed slightly low at the last phase of the bobbin building. That is what has been shown here, that is, we again reduce the speed from 90% to, no, not 90%, by the time we have built 90% of the bobbin and then 97%, then in this process the speed is reduced almost from, let us say, 18,000 to 17,000 rpm. That is how the speed is reduced. Why there is a change in, a reduction in speed? Because there is a possibility of end brakes to increase in the last phase of the bobbin building, which we will discuss, because we will take it up end brakes in a separate lecture. So, we will discuss this point again. Okay. Now, we will discuss estimation of twist, speed, draft and production. How to estimate the twist? This diagram, again the gearing diagram is shown here. In this diagram there are so many gears, and the designer of the drive has kept these 4 gears A, B and C, D as twist change gear. Change of either A or B will change the delivery speed of the front roller. Now, if you let us say, if I change the number of teeth either in A or in B, then if you look at the motion transmission path, that this motion from here goes to A, B, C, D, through this it is going reaching the drafting zone. That means, if I change the gears A or B or C or D any, ultimately the speed of the drafting rollers are going to change. That means, this delivery speed is going to change. However, these gears are not going to affect the speed of the spindle, because spindles are receiving speed from this jockey pulley which is here. So, spindle speed remains constant, only delivery speed by the drafting rollers change, and therefore, twist is going to change. If twist needs to be changed substantially, an adjustment of A, B may not be sufficient, then we change C, D combinations. So, we have these options with us, either we change AB combinations or we can change CD condition depending upon our need. And since all these gears A, B, C, D, all of them can actually change the speed of the drafting rollers, therefore, twist can be changed. Now, twist we all know is the ratio of spindle speed divided by delivery rate. So, twist is spindle speed by delivery rate, or twist also could be spindle rotation per revolution of the front roller divided by delivery per front roller rotations. That is, instead of measuring the actual speed, either measuring or estimating the actual speed, we can also find out twist by finding out that in one turn of the front roller, how many revolutions are there in the spindle, and in one turn of the front roller, how much yarn is delivered. If we take the ratio of these two, we can also find out how much twist is there in a given situation. Now, that is what we have tried to calculate, and that calculation is shown in this diagram, in this slide. Spindle rotations per revolution of front roller. So, what we should do, what we have done here, that we have assumed that this front roller is turning by one revolution. For one rotation of this, how many, what is the revolution of this spindle? So, that means from this side we have to go backwards in these directions and find out how many revolutions are there in the spindle if this roller rotates by one turn. This is the connection, and if I go through these connections, we will be able to find out. That is what exactly we have done. So, it is for spindle rotation per revolution of the front roller will be 1 into 29 by 26, thereby 102 by 103, and then 44 by 30. This is the pulley, whatever is here, and then I have this set of gears A, B and C, D. So, 65 by 72 and maybe 80 by A. Why I have chosen A? Let us say this is the gear, is change gear for our case, that is the twist change gear. Rest of the gears are fixed. So, and then we get 115 by 26, and then here this is 19 mm is the diameter of the valve, and the diameter of the jockey pulley is around maybe 250 mm. So, this will give me the actual rotations of the spindle for one revolution of the front roller, and this value what we get it here is 6807 by A, where A indicates the number of teeth of the change gear, which is twist change gear in this particular case. Now, generally A plus B, summation of the teeth of A plus B, summation of the teeth of A and B is usually 165. This will be given by the machine manufacturers. So, if we take B is 80, then A has to be 85. If we choose B to be 85, then A will be 80, or we could be, there could be certain combinations which have been given by the machine manufacturers, and we can change the teeth of A and B simultaneously, so that the total remains 165. Spindle rotation per revolution of the front roller. Therefore, for the given situation, if I choose A to be 85, then it becomes 80.1. That is, in this particular case, one revolution of this roller will make 80 revolution of the spindle, assuming there is no slippage, there is no loss. Then from the front roller, how much is delivered per revolution? It is, we all know, it is pi d into pi dn, where d is the diameter, which is 27 mm, one revolution, and we have divided it by 1000 to make it into meters. So, we delivered around 0.0848 meter of yarn if the front roller revolves by 1 revolutions, which is equivalent to 8.48 centimeter or 3.33 inches, and hence the twist will become 80.1 divided by 0.0848, and this will be 944 turns per meter. If we convert it into turns per inch, it will give you around 23.98, that is almost 24 turns per inch. Now, if you are interested to know the spindle speed or front roller speed, then we have to start from the motor. We must know what is the speed of the motor, and we have to start from the motor pulley and go. So, because we know the motor is driving all set of gears and the speed is reaching the drafting rolls. So, whatever gears are there in the motion transmission path from motor to the front rollers, all of them will appear in this particular calculation, and you know the gear train ratios. So, if we follow this particular path and consider all those gears which are actually trying to, they are connected and transmitting motion right from the pulley to the front roller, all of them will appear in this particular equations. Then we will get a figure this 247.2 rpm, that is for the speed of the front roller is around 247 rpm, revolution per minute, and the spindle speed in this case will be 1500 is the speed of the motor, then 15 by 15 250 by 21, where we have chosen it to be 21, we have chosen it to be the diameter of the valve. It is shown here 19, but we have chosen it as 21, just an example, we can keep it 19 also. This gives you a figure 17,857 rpm. So, therefore, the spindle speed is this much 17,857 rpm, or if we this figure is going to be basically 21. Okay. Another calculation is winding length per cam revolution. We want to know that if the cam revolves by 1 revolution, that means 1 up and downward stroke, how much yarn is wound. This information is also important for us, and we have tried to calculate this. The change wheels in this case are E and A. These gears are important, and through these gears we will be able to change the winding length per revolution of the cam. Now, the E plus F combination, sum total of E and F is 113, where S is the double worm gear. Length of yarn delivered per builder cam revolution is how much? We want to calculate that if this cam revolves by 1 revolution, then how much length of yarn is delivered. That means, as if the cam is the driver, and from here if we go through this set of gears and reach the drafting roller, front drafting roller, then you will be able to find out for 1 revolution of the cam how much yarn length is delivered. So, all those gears which are connecting cam and the front rollers, they should come into the picture, and this is what we have done in this calculation. Assuming the cam revolution to be 1, we are trying to find out the number of revolutions and therefore, how much is delivered by this front roller. It is going to be 1 into 121 by 2 because this is a double worm, and on the cam is mounted on a wheel which is having 121 teeth, then it comes F by E and then 69 by 103 and then 103 by 102 and then 26 by 29. So, this will give you the revolution of the front roller multiplied by pi into d, and then expressed in terms of meter will give you the length delivered by the front drafting rollers in terms of meters. And this figure is around, for a given situation, F we have chosen as 63 and E as 50, we get a figure 3.92 meter, close to 4 meter. That means, in this case, that is the length of yarn which will be delivered for one complete up and forward journey of the building motions. And the gears which will help me in changing this length is the gear combination E and F. So, adjustment in the ratio of teeth of gears E and F will vary the speed of the builder cam and thus time taken by the ring rail to complete one traverse, because the actual drive comes from the motor through this set of gears to the builder cam. So, if I can reduce the speed of builder cam or increase, that will change the actual up and downward journey, whatever time it needs, that journey actually is controlled by the speed of the cam. So, the set of gears which can change the speed of the cam, these gears will be responsible to change the length that is going to be wound, and in this particular case EF gear combination can do this job. So, more or less yarn will be wound into one layer, that is in one traverse cycle of the ring rail, all depends upon the ratio of these two gears E and F. Draft calculation, now we come. Now, here a diagram is shown, drafting unit of a typical ring frame is shown here, and in method 1 what we can do, number of revolution of the front roller for one revolution of the back roller, if we calculate and assume the diameters of the front and back and middle rollers are all same, then the ratio of revolutions can also give me the draft. So, revolution of the front roller for one revolution of the back roller. So, this is the back roller. So, one revolution of the back roller, we want to know if we go through this set of gears and try to find out how many revolutions are there in the front rollers. So, this is what we have done it here, for one revolution how many revolutions are there of the front roller. So, that will give you 1 into 47 by 21 into 112 by 20. This is a common gear, so it will not come into the picture, and then it is coming H by G. These two are change gears. From here 26 by 29 will give me the speed of the front roller. So, here H and G, these two gears can act as a drop change gear, and if we check these values at 80 and 50, we get a figure 18, which could be the draft in the present case, provided H is 80 and G is 50. Method 2, the ratio of length delivered by front roller per revolution of back roller, that can also give me the draft. That is the ratio of length, how much length will be delivered, that is 17.96 into pi into D3 divided by 1 into pi into D1. That is, if this roller is D1, then and provided D1 and D3 are not exactly same. In the previous case, we assume that the rollers are of same diameter, but sometimes diameter may not be exactly same. In that case, we have to take into account the diameters of the front rollers and diameters of the back rollers also, and if we take into account them, and this equation will come and we will be able to find out the value, provided diameters are same. Otherwise, whatever diameters that D1 and D3 are, we have to put those values and we can find out what is the draft. Break draft, if we want to calculate, procedure is same. Now, the break draft is between back and middle roller. So, in this case we will be interested to know the number of revolution of the middle roller for one revolution of back rollers. And if we assume diameters are same, then break draft is going to be back roller revolution 1 into 44 by 21, and then he will come over here, that is 32 by 71 is a common roller, and here we have another gear. Let us say this is K, then it becomes how much? 67.04 by K. So, that will be your the break draft. If I choose K to be 32, the break draft become 2.09. So, the K is actually here. And for K to be 62, the break draft is going to be 1.08. So, by changing K, we will be able to change the break draft value, but when the break draft changes, because the middle roller speed changes, the front zone draft also will change. And the break draft constant in this case is 67.04 or 67. So, break draft is always in this case is the break draft constant divided by teeth in break draft change pinion, which is K. So, you have to know this is the change pinion in our case, and therefore, the K is coming in the denominator, and hence the break draft is always break draft constant divided by number of teeth in the break draft change pinion. The draft change gears is G and H. So, the gear G affect the speed of the back and the middle roller, because drive is going from the front rollers towards the back. So, if you look at the previous diagram, the motion flow diagram, you will see that it is going from this side to this side always, and therefore, rollers, the speed of both back and middle roller will change simultaneously, and hence break draft is not going to change. And it is not going to change the speed of the front roller also. Therefore, what happened? The speed of front roller is not going to change, and hence twist will also not be changed. But the total draft is going to change, because back and middle roller in combination the speed is going to reduce, and therefore, total draft is going to change, but not the break draft. So, either I change G or I change H. The break draft, that is the draft between back and middle roller, is not going to change. The total draft is going to change, the twist is not going to change. And the break draft change gear, which is this gear, a change in number of teeth in the gear K will change the speed of middle roller, because this gear is going to change the speed of middle roller only, and therefore, the draft in both back and front zone is going to change, because if this speed of this gear is going to change, this roller is going to change, then draft in middle in back zone and draft in the front zone, both are going to change. That is the this is the only difference that you have to always remember, that in one case, if I change K, speed of middle roller will change, draft in the front zone, draft in the middle zone, both will change. The value of K may vary between 32 to 62. The draft in both back and front zone will change and simultaneously, and therefore, there is no change without changing the total draft. So, that is how the role is played by the gear K. in this case. So, it changes the distribution of draft in the two zones. Now, we will see the production calculations. Production per spindle in kg per hour. So, production always means we need to know what is the front roller delivery, what is the time unit, what is the count unit, and what is the yarn count, and what is the efficiency. So, these factors are important: front roller delivery, meters per minute, then time unit is hour, so multiplied by 60, then come yarn count in text system, and then efficiency factor. If these things we take into account, then we can write this is going to be pi drn 10 to the power minus 3 into 60 by 1000 yarn count in text. So, that is what the formula would be, where dr is the front roller diameter in millimeter, n is the front roller speed. So, we can find out this is what is going to be my front roller delivery, and the count is in text, and it basically means weight of 1000 meter of yarn in gram, and we are dividing by 1000 because we want to finally change the unit of gram to kg. Therefore, this 1000 is coming. Now, production calculations, if we go by yarn count and twists, if we given, then delivery rate is the spindle speed by twist, twist is in TPI, and TPI and twist multiplier are related. This formula is also should be known to all of you, that twist is TM, stands for twist multiplier root over NE, that is the count of the yarn in English system. So, production per spindle in that case in gram per hour is going to be this as shown in this diagram. So, this is what the production would be in gram per hour. Spindle speed by twist, that means this ratio will give me the delivery in terms of inches. We have to convert it by 36, convert it into yard, therefore, divide it by 36, and this is per hour, and this is the we have to find out actually in terms of gram, and from the definition of yarn count, if we know the yarn count, we can find it out. This ratio will give me what is there, what is the unit, what is the weight of this yarn that we delivered in 1 hour, and that multiplied by the efficiency will give me the production. So, this is what is shown here, the same formula we are showing it in terms of 7.2 is a factor spindle speed by TPI 1 upon yarn count and multiplied by efficiency factor. Efficiency is 80%, then we have to be 80 by 100, that is 0.8, we have to multiply to get the proper production. Now, another thing is, if you want to replace TPI by Tm into root over NE, then we can write Tm into root over NE, the same formula written in different ways, so that you get a complete understanding that how the different parameters are affecting the productivity. So, here Tm is here. Now, in this equation you see there are so many things which are constant, like spindle speed we write it in terms of U, spindle speed in thousands RPM. So, suppose the machine is running at 18,000 RPM. So, U is in this case will be 18, and yarn count in NE. So, the NE is coming here and here, root over NE and NE. So, it will be 7.2, let us say this whole thing is a constant. So, it can write some constant K U E and Tm NE to the power 1.5. This whole thing becomes my production per spindle. So, that constant is basically in this case 7.2 by 100 in the present case. So, here if we look at this equation, we can say that productivity is directly proportional to spindle speed U, which is in terms of 1000. It also proportional to the efficiency factor, it inversely proportional to Tm, and if we increase twist multiplier, the productivity is going to reduce. The other thing is that it is proportional to the yarn count to the power minus 1.5. That means, if we change the yarn count, if I make it finer or coarser, there will be a tremendous influence of it on the productivity of the machine. So, this gives us the an idea or that how the productivity is going to be affected by three important parameters: speed of the machine, the twist multiplier, and the count of the yarn. Yarn content in a ring frame corp. We all know the shape of the ring frame corp. According to CITRA, there is a norm, and they have found out that the yarn content in gram is 3.25 into L into d square. This is an empirical formula, where L indicates the spindle lift in inches and d is the ring diameter also in inches. Both are the units are in inch. So, if the spindle lift is 7 inches, ring diameter is considered to be 7.75 inch, the yarn content we can find out, which is going to be 69.67 gram in the present case. So, this is an approximate formula which is practically very useful in the industrial situations, and this is what has been found out by the CITRA, and this can help us to know the content of a yarn when we know the ring diameter and the lift, total lift. With this, we close this particular discussion.